Alright, so I'm doing kind of the last of our classic iterative algorithms where we're actually given the algorithm here. So this one is another uneven step one. So what we've got is I equals 2 while I is less than n, do I is equal to, or whoops, I is equal to I times I, and x is equal to x plus 1 or x plus plus. And so this is our kind of very unevenly stepped algorithm where it's actually squaring each time. And this is very, very similar kind of in practice to the last one where it was instead I is equal to I times 2, which was our kind of other uneven step, except this time it's squaring every time, not just multiplying by 2. So the actual structure of the sum formula here is really simple, just like last time. So I equals 1 to k of 1. And why does I equal 1? Here, I equals 2. This I is not that I. You could even use a different variable to denote it. This is literally just counting the number of iterations. We're saying, okay, the first time through, it does it once. The second time through, it does it once. The third time through, it does it once. We're just counting the number of iterations, so the correlation is a bit broken there compared to the previous ones where we map that number down directly. But due to our sum formulae, we do come out with the exact same answer, that this is just k, or k minus 1 plus 1, so k. So just like with the previous uneven step of I equals I times 2, we're kind of left with the more fundamental question of what is k, and what is its relationship to n. So if we want to actually put down here like our n, of what the value will actually be at that value of n, or how many iterations it would take to get to that value of n, and let's just call the iteration count k. So on our first iteration, I is going to start at 2, and then it's going to square, so n is going to be 4. On our second iteration, n is going to be 4 squared, is going to be 16. On our third iteration, n is going to be 16 squared, which is 64, and no, wait, is that right? No, sorry, 256, not 64. So obviously that climbs crazy fast, and I'm not even going to go past that because these numbers get huge. So obviously this is k and this is n, where this is squaring every time. It's 4 squared, 16 squared. So if we try to express this in the way that we had previously, so our previous attempt, what we tried to do was say, okay, maybe this relationship here looks something of the form 2 to the something. So let's try that again here. Okay, well 4 is 2 squared. Maybe that's relevant. Actually, let's just draw it on the side here. So this could be represented as 2 squared. 16 could be represented as 2 to the 4. And 256 could be represented as 2 to the 8. Well, that's not really helping us that much because this number isn't changing constantly. This exponent is doubling every time. But if we remember what our formula was last time, that it was doubling every time, last time it was doubling every time, it was 2 to the k that was the answer. So if we actually extract this, just like squared is kind of one tier higher than just timesing by 2, if we actually give these exponents another tier, let's try 2 to the power of 2 to the power of 1. Obviously this 2 to the power of 1 is 2, so this is 2 squared, which is 4. 2 to the power of 2 to the power of 2. So now we've got 2 to the power of 2 to the power of 2, which is 4. So 2 to the power of 4 is 16. 2 to the power of 2 to the power of 3. And 2 to the power of 3 is 8. These are the same. That gives us 256. So the actual relationship, and I'll just highlight this in color, that we found between n and k at each iteration is this second exponent. So rather than just rising by a set power every time, it's actually rising by a power to that power every time. And if this continues, that correlation actually continues. So the relationship that we end up with here is that n, whoops, we can go back to light gray now, n is equal to 2 to the 2 to the k. That's just a little bit ugly. K to the k. And that's definitely something we haven't seen before, but the answer is actually not that difficult. You can just view 2 to the power of k as a single exponent, or if you like, we can extrapolate that. Let's say we just let 2 to the power of k equal just a new variable g, or just anything. We just make up a variable just so that it looks like something we're a little bit more familiar with. We can say, okay, n is equal to 2 to the g, where g is equal to 2 to the k. So that's a direct substitution, that's all fine. How would we rearrange this in this case? And well, in this case, if we wanted to express something in terms of g, we could say, oh, okay, cool, log base 2 of n is equal to g, remembering where g is equal to 2k. So if we want to substitute that back in now, we totally can. So if we actually scroll down here and we say, okay, remember that g is equal to 2k. Now that we've made that the exponent, we want to bring this back in. We can say log base 2 of n is equal to 2 to the power of k. And so now that it's in this form, we can go one step further. So just as if this was a normal exponent, like if this was 8 or something, it's the exact step that we've just done above. So now if we want to find out what k is equal to log base 2 of n. And that's basically our answer. So if we obviously bring this all the way back up and substitute up here for k, our sum formula just counts one basic operation is being performed each time it iterates. Then our answer is that the cost of n is equal to log base 2 of log base 2n, which, if I just clear a little space here, I can write belongs to theta g of log n. That's super messy, sorry about that. But that's basically our calculations for how we work out I is equal to I squared, and that's actually how we end up with a formula which comes out as log n.